Hey, good afternoon, everyone. This is the Infinite Group. Today we're going to be presenting our final project as of now, which is a procedurally generated racing game. My name is John, and I'm going to be providing the high level overview of our technology and also talking about some of the specific technologies that I've been working on. So, a lot of our work these past couple of weeks has been deciding our system and the abstractions that we're going to put in place. So, to represent our world, we've decided to create a collection of a few predefined biomes. Each of those biomes are going to have a certain artistic direction, and they're all going to share the same random variables when they generate their noise functions. And each biome is a collection of chunks, and a chunk is derived by first subdividing a flat plane and then generating a matrix from that. And from that matrix, we walk over each of the vertices and then sample a noise function. In this case, we primarily use the Perlin noise built into Godot's fast noise light library. And then we set the Y value based on the value of that noise. And this creates what's called a height map, which has a similar effect to this. And we apply that height map matrix to a collider and to the surface of the plane, and that creates a collidable terrain. Now, this is a whole lot of computation, and you can imagine running this all sequentially on the main thread created lag spikes. So we've opted to create a job scheduling system and multi-threading, which allows for a lot of parallel pre-computation. So we first pre-compute the scene tree for each of the chunks, and we also pre-compute all of these noise values in parallel whenever a biome needs to be generated, and then add these all to a map of chunks. And then once the player requests a chunk, then it just simply indexes into the map and then instantiates that in. The other thing that I've been working on is some sort of object placement algorithm. This uses a noise function such as Perlin and creates a height map, and then we set cutoffs on that height map depending on whether or not we place the object in. And the level of granularity based on how many samples and subdivisions we take allows us to fine tune the lushness of the world.
Hi everyone, I'm Adney. For this effort in our project, I was responsible for two main things. One was setting up the stage for procedural generation, and two is an optimization we made for biome stitching, which is an implementation detail we will come to later in this presentation. In order to set up the stage for procedural generation, we first needed a very basic setup, which consisted of a multiplayer level environment. This environment houses all the multiplayer networking logic, as well as the checkpointing logic when it comes to racing, and the respawn logic for if the player falls off the track and needs to respawn. As for the actual arena, in order to build procedural generation smoothly, we needed two custom objects, one being the procedural plane. In this object basically houses all the vertices, and then we perturb these vertices and apply that as the surface for the terrain. On top of this procedural plane object, we intend to place another object called a biome layer object, and this biome layer is responsible for placing all biome specific objects on the procedural plane. And so it'll have access to the vertices in the procedural plane, and a couple of noise functions to determine how to scatter the objects on the plane and how to place them in with respect to their y position and stuff like that.
My name's Geronimo, and one of the things I worked on for this project is the biome stitching. So a biome is defined as three chunks that share the same amplitude, noise seed, and octaves. To make the transition between the biomes seamless, we used a blending zone. This zone covers the last half of the final chunk in the current biome and the first half of the first chunk in the next biome. In this blending zone, each vertex gets a blending factor that ranges from 0, meaning it fully belongs to the first biome, to 1, meaning it fully belongs to the second biome. We use this factor to apply linear interpolation to calculate the y values for the vertices. This creates a smooth transition without any sharp changes. This diagram shows how the biome staging works. On the left, we have biome 1, and on the right, biome 2. The blue section in the middle is the blending zone. The blending factor, shown by the green arrow, starts at 0 at the beginning of the zone and increases to 1 by the end. Using linear interpolation, we calculate the height values in this area by blending the two biomes together. This ensures the terrain transitions smoothly without any noticeable breaks. This process keeps the track visually cohesive and functional as players move from one biome to the next. Here you can see the player transitioning from a lower amplitude biome to a higher amplitude biome. The blending zone in the middle ensures that both are blended together to create a seamless track.
Hi, I'm Mark, and for our project, I've worked on a couple of things: texturing, audio, and lighting. Here I made materials for different objects in the game and added audio for interactions. Player camera controls, I added all the player movement, making sure everything feels responsive. I added controller support through Godot. Networking, I made a lot of progress on synchronization. We finished working on Dead Reckoning to predict player positions, and used a LERP to further smooth out our Dead Reckoning. Menus, made a menu system. Everything communicates via signals. It's basic and it works. It allows you to resize and everything's still good. And I'm working on a skinning system to let each player select their own skin that they want in multiplayer or single player. And for texturing and audio, here's a little example. Here's an example of my bounce sound.
Boing.
And that's about it for that. For networking, I worked on state synchronization. Here in orange, you can see the Dead Reckoning, where we tell the physics engine what info it needs to do the physics calculations. Here in red, we get the calculated position, and here in green, if the distance between it and the actual position it should be at is far enough, then we LERP it together.
So like we mentioned in our presentation, we are just basing this off of our existing game, so we have all of those existing features. Right now we're focusing on the single player experience for our procedural generation, and we haven't focused on the art necessarily for this, more the technology. This is a demonstration of us using the Perlin noise function built into Godot and applying that to our plane, which I've detailed in our write-up. And also I use that same random height map to generate objects within the world, and all of these variables are tunable. So as I progress along the level, I reach a certain point and our script determines that it needs to place in a new chunk. The stitching itself is very seamless. This is a demo of how you can really tune the variables to get very different types of terrain.